Hi, my name is Ramon Lopez. I'm a professor of physics at the University of Texas at Arlington in Arlington, Texas. And today I'm going to talk about energy in magnetic fields. This is another in the series of content support lectures that we are doing to support our workshops on instructional materials that have been developed by a partnership between AAPT and Temple University and NASA through the NASA Space Science Education Consortium at Goddard Space Flight Center. And the various people that are involved in the team are listed here in this first page. Myself, Bradley Ambrose, Janelle Bailey, Chimena Sid, Darcy Donnellan, Rebecca Vieira, and Shannon Wilpley. So we represent this team working through AAPT to develop these instructional materials and to do these workshops. And with each workshop, we provide a short piece on some of the science behind what's going on in the activity. So today, we're going to be focusing on magnetic fields. And I want to start with just a brief overview of magnetic fields. We know that magnetic fields are generated by currents, where current is electrical charge in motion relative to the observer, or an electric field that's changing in time, the so-called displacement current. And the mathematical relationship between current and magnetic field is given by Ampere's law, and the displacement current was an addition provided by Maxwell to take into account time changes in the electric field and to resolve some of the questions about magnetic fields, say, generated around a capacitor. Now, permanent magnets, the kind that you might use on your refrigerator door to hold something up, those create magnetic fields by aligning the magnetic moments of atoms and materials, because all subatomic particles have a magnetic moment, and atoms then will have the sum of the magnetic moments of those particles, plus the magnetic moment generated by the net angular momentum of the electrons in their orbits and the magnetic moment of the nucleus. All of that adds up, and certain kinds of materials can align those magnetic moments in domains within the material to make large-scale macroscopic magnetic fields. Mostly materials, the magnetic moments are all pointing in different directions, and so they add up to zero. But magnetic fields can be created in permanent magnets, and it's essentially little currents, if you will. And you can describe permanent magnets in terms of macro scale currents, volume currents, surface currents that aren't really currents like you have in the lab, where you hook up a wire to a battery and you turn on you flip the switch and current runs through the wire. When you do that in the lab, you get a current that makes a magnetic field that's consistent with Ampere's law. So there's a fundamental question about magnetic fields and work. Do magnetic fields do work? Because the fundamental equation for the magnetic force is the force is equal to QV cross B. So it's the charge times the cross product of the particle's velocity and magnetic field. So the magnetic force is always perpendicular to the motion. And so magnetic fields never do any work. But you might say, well, what's going on here? Two magnetic fields can repel each other. So I can take two magnets and push them close together and let them, and they're, say, north and north facing poles. So I can feel that I'm doing work when I push them together. And then when I let them go, they repel each other. Well, how did that happen? Where did that energy come from? How was that work done? Well, the answer is that when you change the magnetic field, it produces an electric field. And it's the electric field that actually does work. And so all of the changing magnetic fields are producing electric fields, and the electric fields are the ones that are actually involved in the conversion of energy. And this allows us to understand how and where the energy goes in simple interactions with magnets. Because when I started pushing those magnets together, the two north-facing poles, I was changing the magnetic field. And in doing so, I was creating an electric field, and I was doing work against that. So I can do work against the field and store energy in a magnetic field, even though the magnetic field itself does no work. Now, in university physics, you'll learn about inductors, which, like capacitors, can store energy. And that's usually where discussion of magnetic field energy sort of stops, that there's a density of energy, the energy per unit volume. If B is the magnetic field in MKS units in Tesla, then it's B squared over 2 mu naught. Now, mu naught is 4 pi times 10 to the minus 7 in MKS units. So 1 Tesla actually is a lot of energy per unit volume. A Tesla is a very large unit of magnetic field. And on the surface of the Earth's magnetic field is much, much smaller than a Tesla. So, a Tesla is a big unit. Now, the next generation science standards and the framework for K-12 science education, on which the NGSS is based, place a lot of emphasis on energy in fields. Because if you don't consider the energy in fields, then there are interactions that are more difficult to understand, like a simple attraction or repulsion of electrically charged or especially magnetized objects. If I take a magnet and pass it over some paper clips and a paper clip gets pulled up, how did that happen? What's the energy transformation that's going on there? And it turns out also that the energy in fields is very important for understanding the fundamentals of chemical interactions, how chemical interactions work and why bonds don't actually store energy. You get energy in a chemical reaction by moving from one bond strength to a stronger bond strength. So you're going further down in terms of the energy necessary to pull objects apart. And that's the source of energy in chemical reactions, is going from loose bonds to stronger bonds. So the energy is not stored in bonds. It's actually exactly the opposite. It takes energy to break bonds. And the stronger the bond, the more energy it takes. It also turns out that this concept is applied in what's called the mass difference in nuclear physics, that many students have difficulty with when they learn about it in university, that the mass of a nucleus is less than the mass of the parts. Well, where did that mass go? It was released as energy when the nucleus was formed. And so to separate all of the protons and neutrons in the nucleus, you have to put that energy back in. And that energy then appears as mass in the particles. So this concept of energy in fields is a pretty important one, and it's new compared to the way physics in high school certainly has been taught for ever, really. And also, energy in magnetic fields is fundamental to understanding the space environment and the dynamics of the sun. Now, Faraday's law of induction with Lenz's law, and Lenz's law gives you the minus sign there, tells us that the induced voltage and the current that it drives in the conductor opposes the change in the magnetic field. So if I try to change the magnetic flux, the amount of magnetic field going through a loop, along the edge of the loop, an electric field is generated, the inductive electric field, which then drives a current that tries to oppose that change, and that's that minus sign. But if this happens in an infinitely conducting material, then every change in the magnetic field would be completely opposed. And the magnetic field would never be able to change. The magnetic field would be frozen into the conductor. And any motion relative to the magnetic field in the conductor would result in an inductive electric field that just opposes the change. And that's what happens in space plasmas, is that the particles in a plasma, the protons and electrons primarily, are free to move. And so it's essentially like infinite conductivity. And so if I try to change the magnetic field, an induced current appears that cancels that change. And so the magnetic field is frozen into the plasma. So where the plasma moves, the magnetic field has to move with it. And the plasma can move under forces like gravity or a pressure gradient or other forces that would cause the plasma to move, and the magnetic field would move with it. So in space plasmas, we have what's called the BV perspective. That yes, currents make magnetic fields and electric fields drive currents. So E and J being the current. But in space plasmas, those quantities are set by other parameters. So there's something called the BV perspective, B magnetic field and V the velocity of the plasma. So the plasmas will be under various forces and they will move in response to the net force applied to the plasma. And then the electric field is just what's needed in the observer's frame of reference to account for that motion. Because if I see a plasma and magnetic field moving past me, then I see that motional electric field. If I'm in the frame of reference of the plasma, if I'm moving with the plasma, I don't see the electric field. And so electric fields are completely dependent on your frame of reference in motion. And so the plasmas will move, and they're dragging the magnetic field with them. So that creates the magnetic shear, that creates the structure of the magnetic field. And the curl of the magnetic field is what gives the current. And that's Ampere's law, turning it around, that the curl of magnetic field is the current rather than the current generating the magnetic field. And it works this way just because of the scale of the system in space. Yeah, here in the lab, I flip a switch and I put a current through, and the magnetic field adjusts to that current so that it matches Ampere's law. But in space, it's the time scales are such that the current will adjust to the change in the magnetic field first. And so in space plasmas, if you just know what the magnetic field is, then the current is what is consistent with that. It's the curl of the magnetic field. So why don't stars freeze? Because if the plasma is moving and dragging the magnetic field and twisting it up, that represents stored energy. Just like if I take two north poles and push them together, that represents stored energy. And that energy has to be released. But if the magnetic field is frozen into the plasma, if it can't move, if it can't get, with magnets, I can let go of the magnets fly apart. But in space, how does the plasma let go? Well, there is a process for that called magnetic reconnection. Because if it wasn't for that, then all of the motion eventually of plasmas, all of the boiling and churning inside of a star would be turned into magnetic energy. And stars would literally freeze with all of the motion of the plasma going into the magnetic field. So something has to allow the energy to be released from the magnetic field. And that is this process called magnetic reconnection. There's a NASA spacecraft mission that's actually 4 identical spacecraft flying in close formation that has been uncovering a lot of the secrets of magnetic reconnection. And, there have been lots of theories, and people have debated what's really the most important part of the process. And we're starting to understand that much better now because of the magnetospheric multi-scale mission. And this diagram illustrates what happens is that when you get regions where the currents are very intense and things are changing over a very small spatial scale, first the ions let go of the magnetic field because they can't gyrate around them anymore. They're acting like free particles. And finally, the electrons do the same thing, which do it on a much, much smaller time or much faster time scale and also much smaller space scale, because the electrons are so much lighter than the ions. They have so much less inertia. But at that point, now the magnetic field can decouple and its energy is released through, the magnetic field is changing. So in time, so it creates an electric field, which then is able to put energy into the plasma, and magnetic energy then disappears and appears in the form of plasma energy. This is a fundamental process in the universe. And it happens on the sun to power solar explosions and release coronal mass ejections from the sun, these big clouds of plasma and magnetic field, and the energy that's released by magnetic reconnection in loops of magnetic field close to the sun, that provides the energy for solar flares. And then at Earth, it's magnetic reconnection which dominates the transfer of energy from the solar wind to Earth's magnetosphere. And so that is what is powering magnetic storms here on Earth. There's reconnection on the day side between the solar wind and the Earth's magnetic field, and that interconnects the Earth's magnetic field with the solar magnetic field, allowing the energy to come into the Earth's magnetosphere, allowing the solar wind flow to drag plasma in the ionosphere, starting currents flowing, and then finally the magnetic field reconnects again in the tail, releasing more energy that will power aurora and other kind of phenomena like that. So it's a pretty fundamental process, and it's actually best studied here near Earth. So it is a fundamental process, and the magnetosphere multiscale mission has made great progress in helping us understand the details of magnetic reconnection. And you can go to mms.gsfc, that's Goddard Space Flight Center.nasa.gov, and read all about magnetospheric multiscale and the science that it is doing. So to conclude, without the concept of energy and fields, there are a lot of everyday phenomena, particularly involving magnetism, because magnetism is something that you can sense, and you can actually feel the forces between two poles of a magnet. Either they're pulling together or they're pushing apart. You can feel that there's something there in between them, some invisible thing. And unless you have the concept of energy and fields, then there are simply a lot of things that you can't adequately explain. You can talk about potential energy and things like that, but it's just it's more difficult to understand. And the transfer of energy from plasmas to magnetic fields and back to plasmas, so that's a fundamental piece of the dynamics of the space environment everywhere in space, everywhere in the universe, not just in our solar system. And the magnetospheric multiscale mission is uncovering the secrets of magnetic reconnection. And it's reconnection that allows magnetic energy that is stored by the motion of plasma to be released back to the plasma. Thank you.